Morning, good afternoon, good evening, everyone, whatever your time zone is. My name is Dr. Luca Matra, and I'm a lecturer in astronomy at the National University of Ireland in Galway, in Ireland. So the goal of this lecture is for you to get a more tangible, more practical view of what an interferometric data set looks like, and in particular, we're gonna start from a calibrated data set. So you've already gone through the calibration in the Mir software package, and we're now going to look at how to interpret the calibrated visibilities that we see without or before we carry out any imaging, for example, through the clean algorithm. So you've already seen how to calibrate, how calibration works out to get from a raw visibility data set to a calibrated visibility data set. So now let's get a pictorial view of what a calibrated visibility data set looked like. So we start from the UV coverage as shown here in this picture. So basically this is a map of Fourier space in U and V coordinates. So the U and V coordinates are measured in units of, so this is probably a recap, you've probably seen this before in the lectures, but just to make sure. So U and V are the UV coordinates in units of kilolambda, i.e. thousands of wavelengths. So basically a point that is, so if you have an SMA baseline of 13 meters, okay, and you're observing at a wavelength of 1.3 millimeters, you will be at a UV distance of 10 kilolambda, okay, 10,000 wavelengths. And 13 meters divided by 1.3 is 10. So you'll be at 10 kilolambda. So it will be a point somewhere in here. Now this UV coverage is basically a collection of UV points corresponding to single measurements by the telescope. So every point on this diagram is corresponds to a pair of antennas making a single baseline per time per frequency, because different times correspond to different UV points, and different frequencies also correspond to different UV points. Okay, so let's get started. So what you've seen before is that through the Van Cittert-Zernike theorem, you can connect the 2D brightness distribution, or the sky image, which we call a function t, as a function of L and M, which are the array and deck coordinates in the sky. You can transform that to a 2D visibility function, big V, as a function of UV coordinates U and V, through the Fourier transform. Okay, so what the interferometer measures is the Fourier transform of the sky brightness distribution T. And the two are, as I just said, the two are related through the Fourier transform. So the visibility function is the Fourier transform of the image function, and the image function is the inverse Fourier transform of the visibility function. Now, what I would like to underline here is that the visibility function is complex valued. It's a complex function, and what that means is that it has real and imaginary parts, or equivalently phases and amplitudes. And again, you will have seen this before. And what I would like to point out, you might not have seen this before in the lectures, but basically it's a reminder to Euler's formula, which you will have all done in your undergraduate degrees, where for a complex number we can express this as e to the I x, which we can express as cos x, which is the real part, plus I sine x, where sine x would be the imaginary part of the complex number. Okay, and so the complex number c e I phi, so we can represent our visibility as a complex number c e I phi, which has c being the amplitude and phi being the phase. So c cos x will be a real part, and c sine x will be, c cos phi, because it will be phi here, c cos phi will be your real part, and c sine phi would be your imaginary part. And you can use this Euler formula to go from phase and amplitudes to real and imaginary at any point. Okay, but since we'll be talking about both, I thought I should remind you here. Okay, so for every discrete point in UV space, okay, so because remember, we're not taking measurements. We don't know what the visibility function big V is everywhere in this UV space. we only measure it at discrete points which are represented by this UV coverage. Okay, so for every discrete UV point, the interferometer measures the real part of the visibility function and the imaginary part of the visibility function, or equivalently the phase and the amplitude of the visibility function. And the other thing that we can estimate for every point is its uncertainty. So the uncertainty in the real, which is equal to the uncertainty in the imaginary part of the visibility function, and this uncertainty can where did that go? Oh, well, anyways, and this uncertainty goes into this weight W, where the weight is 1 over the uncertainty squared for a given visibility data point, right? So after you do all of your calibration, what you end up with for your source, for your science target, is a calibrated complex visibility function, which is evaluated at this discrete UV points. In practice, this sounds very complicated, but really all you have is a big table of values where you have columns being U and V, so the coordinates of the visibility data point, and then the measurement, the real and imaginary part of the visibility function, and their uncertainty represented through the weight. Okay, so basically all these data points, U0, U1, U2, Ui, all the way to UN, basically represent the collection of all of these points in the UV plane with all of their measurements. Okay, so where n is the number of baselines. So the number of baselines is expressed as the number of antennas multiplied by the number of antennas minus 1, all divided by 2. In reality, there are twice the number of data points as the number of baselines. So sorry, the number of data points in this UV coverage is twice the number of baselines, and that is because the visibility function is Hermitian, because it's the Fourier transform of a real valued function, which is our image function. So our function T L of M, which represents the brightness distribution of our source in the night sky, is a real valued function, and its Fourier transform is therefore Hermitian. What does it mean that it's Hermitian? It means that basically a point at plus U plus V, let's say up here, a point at plus U plus V has the same real part as a point at minus U minus V. Okay, so they have the same real part, but the imaginary part of the point minus U minus V is the negative of the imaginary part at plus U plus V. That's what it means for a function to be Hermitian. So basically for every data point at plus U plus V, we also know its real and imaginary parts at minus U minus V. We don't need to sample it twice. It's the same point. But therefore you end up with twice as many points as your number of baselines. And of course, this is strictly speaking for a given point in time and for a single frequency. In reality, if you've got multiple scans over time, which will always happen in interferometric observation, and multiple frequencies, you will have that your total number of points in this table will be the number of baselines multiplied by 2, multiplied by the number of times, by the amount of scans, and multiplied by the number of frequencies that you have in your observation. So it can be a very big table, but it's not. I just wanted to kind of convince you that it's not scary at all. Okay. So again, as a reminder, you will have seen this in your imaging theory lectures. These are the Fourier pairs. So this is very, very important to remember. So these Fourier pairs are very important to remember to be able to interpret what you see in the visibility plane. So in your visibility data, you need to be able to interpret that without needing to make images. Okay, so you'll have to remember that if you see a DC constant value in the real part of your visibility function, that corresponds to a point source or a delta function in the center of your image. So if you have a point source in the center of your image, imagine you have an unresolved astrophysical source. It will what will it look like in the visibility data? It will look like a constant at all UV points. Okay. If you have a small Gaussian, so a compact, but say resolved source, it will become a big Gaussian in the real part of the visibility function. If this Gaussian is inclined, so imagine, that you have a kind of an elongated Gaussian, that will also correspond to an elongated Gaussian in visibility space, but it will be 90 degrees rotated. Okay, that's just the Fourier property. And similarly, if you have a uniform disk where the brightness is uniform inside it, and then there's a sharp cutoff, that corresponds to a Bessel function when applying the Fourier transform, and therefore in visibility space. So one important thing to remember is that the amplitude, so here we've looked at the real part of the visibility function, but just a reminder that the amplitude in general tells you how much flux comes from your source, and the phase tells you more or less where the flux is. Okay, so if the source is symmetric, so centrally symmetric, and is centered at the origin, so at the center of the image, or at the face, or the so-called face center of the observations, then the phase will be zero everywhere. Again, I'm not showing the phase here, but just keep in mind that the phase will be zero everywhere. And the real part of the the real part of the visibility function will be equal to the amplitude of the visibility function. And that this just comes from Euler's formula, okay? So if the phase is zero, then you get that the real part is the same as the amplitude, okay? So in these cases here, where the source is centrally symmetric and at the center of the field, then this real part of the visibility function that I'm showing will be the same as the amplitude of the visibility function, okay? And remember, these visibility functions that I'm showing here are sampled everywhere, so you can basically see their value, you can get their value everywhere, so they're a continuous function, but in reality, an interferometer only samples these functions at discrete points which correspond to your UV coverage, okay? So the coordinates here are dec and RA in the image, and then become phi and u in Fourier plane, and so we're only sampling them at the UV coordinates of our observation, and it's also a finite number of UV points, which is another important point. So if the source is instead not centered, so what we said is that if the source is centered, then the amplitude will be the same as the real part, and the phase will be zero everywhere. Okay, so here I'm showing now amplitude and phase. So if we offset, for example, a Gaussian from the center of our image, the amplitude will stay the same. So it will be the same as a source that is centered at the phase center, but the phase will not be zero anymore because the source is offset towards the top right, i.e., which will be northwest in an astronomical image. And so what we will see that the phase will follow a sinusoidal function that is generally called a wrap. So we will see wraps in the direction of this offset. Okay. So after the short introduction and a little bit of revision of Fourier properties and how to translate image properties into Fourier properties and vice versa, I'm going to guide you through this Jupyter notebook where we're going to get a little bit more familiar with these concepts and with picturing what calibrated visibility data really looks like using true visibility data, in this case from ALMA, without having to rely on imaging and the cleaning process. So first of all, we're going to import. I'm going to run this live as I speak. So first of all, we import some. Oh, and I should say that this script will be available for you to play with online. You can download it, modify it, and you can grab it from my GitHub and play with it yourself to get familiar with some of these concepts. Okay, so first we import some Python packages, then we're gonna read in some ALMA interferometric data that I got back in 2016, which observed the nearby star Vega, and this data was taken at 230 gigahertz, so 1.3 millimeters. And in this first step, I'm basically just reading in this data where I had already saved this data beforehand as a numpy .npy save file containing a table with columns U, V, real, imaginary, and weight. So this is exactly the table that I was talking to you about in the slides. containing all of these, each of these columns. And then the final thing I'm doing here is basically injecting extra flux in the star to make it brighter and more obvious, so that it becomes clear when we look at the visibilities what we're trying to get to. So, but bear with me there. So the first thing we're gonna do. So this is exactly like calibrated visibility data you may have for your own source. So once you read it in Python in one form or another, you can get an idea of for example, the UV coverage. You can do this also through CASA tools, but I'm just doing it here in plain Python. So you can get an idea of the UV coverage for the specific observation. So here's an example. And so this is exactly the UV coverage that we were looking at on the slides. There is a difference though. You can see that the shape is quite different. Is quite different. So what I'm doing here is, if you look at I'm just plotting the U and the V coordinates. So these are the coordinates of our observations with the same color everywhere, and with some level of transparency. And so what you see is that there is some structure which is more elongated along the east-west baseline direction than the north-south baseline direction. So I'm just gonna spend half a minute kind of explaining to you why that is. So let's see. Here we go. Okay, so you can find also the Jupyter Notebook at this website where you can run it. Okay, so the reason. Okay, so let's just go back quickly. Yeah, so the reason that the UV coverage is elongated along the east-west direction compared to north-south direction is because Vega is a very northerly star, and as observed by ALMA in the southern hemisphere, the star only rises above, only up to 30 degrees above the horizon. So it's quite low in the northern, towards the north in the sky as seen by ALMA. So imagine 3 antenna in the ALMA array. Okay, so you've got an east-west baseline, B12, and then you've got a north-south baseline, B13. And remember, when we go from baselines to UV distance, what really matters is not the baseline itself, but rather the projected baseline. So basically the baseline projected against, as will be seen from the star. So if you were sitting at the star looking at the antennas, you would see for the north-south baseline, you would see a very short projected baseline because the star is very low in the northern sky. Whereas for east-west baselines, you would see a projected baseline that is basically the same as the actual distance between the two antennas. So what that will mean is that the UV distance corresponding to these projected baselines would be the same as the baseline for east-west for the east-west direction, and it would be a much shrunk projected baseline. So B13 projected is much smaller than the actual B13 north-south baseline, whereas the B12 projected baselines east-west is basically the same as the actual baseline. So what that means is that if you're looking at a source that is very low in the north from ALMA in the southern hemisphere, you will basically have very shrunk UV distances in the north-south direction and broader UV distances in the east-west direction. And that is exactly what we're seeing. Okay. Well, yeah, that is exactly what we're seeing. We're seeing a more elongated UV coverage in the east-west direction and a shrunk UV coverage in the north-south direction. Now, what you can also see here is that you can see kind of that there are tracks. So let's see. Let me pick some more obvious ones. So here, for example, well, yeah, you should be able to see it. So here you can see that there are 4 tracks. Okay, so these 4 tracks actually correspond to one baseline as it changes a function of time as the Earth rotates. So each little symbol, each point here is a point in time and a point in frequency, remember, for a given baseline. So you can see that there's 4 pretty much parallel tracks. These tracks represent the 4 frequency spectral windows of ALMA. Okay, so these are the same baseline. So these parallel lines are the same baseline, but at different frequency, observed at different frequencies. Whereas along the track is basically the same baseline at the same frequency as a function of time as the Earth rotates. So the Earth's rotation will basically spread out a longer baseline much more than it will smaller baselines. So that's why the points look denser and darker here in the center for shorter baselines compared to the longer baselines. So that's what we're seeing there. Okay, so if we go down, now we're going to plot the. So what I'm going to do here is what I used the same color for all of the baselines. Okay, but now I'm going to use a color scale to represent the real and imaginary part and the weight of the visibilities. So the real part, you can see that it's the most obvious thing here is that it's pretty much blue all the way across. So if you look at our color scale goes between about -50 to 175 millijansky, but we can see that most of the values are around this blue color, which is around 100 millijansky, which is what we would expect it from the flux of the star. And what does this tell you? So if you had data that you didn't know what it contained, and you saw that, and you opened it, and you saw that the real part is constant everywhere, what you would deduce here is that you're looking at a point source, right? Remember our Fourier pairs, a delta function on resolved point source corresponds to a constant in the visibility function, okay? And then next we look at the imaginaries here, and you can see that also the imaginaries are all around the same color, which corresponds to this value of around 0 in the imaginary part, from which you would deduce that this point source is, I should leave it to you, but since we're not in a live format, I'll just tell you, which means that the source is well centered at the face center of these observations. And finally, we can look at the weight. Remember, the weight is 1 over the uncertainty squared. Okay, so the higher the weight, the lower the uncertainty. The lower the weight, the higher the uncertainty. So what you can see here is that in a given track, remember I told you that in a track is basically the same baseline as a function of time, and parallel tracks are at different frequencies. So here, basically what we're seeing is that as a function of time, the weight is going up, which means that the uncertainty is going down, which could be which is probably due to a lowering in the system temperature. Remember, I think you will have seen in other lectures how the weight is represented, or how the uncertainty comes from the system temperature of the system. And that lowering of the system temperature and of the uncertainty probably comes from the fact that either the weather got better, or basically we're observing through less of the atmosphere. So if the source was rising in the sky, we're observing through less and less atmosphere as it goes up. So basically the amount of noise will go down. So you can see that this weight varies depending on the UV point. And from its value, which is around, let's say, 0.01 to 0.07, that indicates a level of uncertainty of about 1 over the square root of weight, which is 4 to 10 millijansky per UV point. Now, what I did at the beginning is I increased the stellar flux to by hand artificially to 100 millijansky from what it was before, which is around 2.5 millijansky. Why did I do that? Because if the flux of the star was 2.5 millijansky, but the noise is 4 to 10 millijansky, so the noise is larger than the stellar flux, all you would have seen here, for example, in the real part, is you would have seen just a lot of noise going around. And you can still see a little bit of noise. You can still see a little bit of noise there. If I zoom in, you can see that this is not just a constant color. It's around 100, but it hovers around 100 due to the noise in the real data. Okay. Now, one thing you can do to decrease the noise level in a real scenario. Also, the imaginaries obviously are 0, which means that not only is it centered at the origin, but the source is also centrally symmetric. So if you have a centrally symmetric source, it is usually useful to plot the real and imaginary components of visibilities, not as a function of UV distance in 2D, but rather in 1D as a function of distance from the phase center. Okay, so what we can do where this distance from the face center is simply the square root of the u coordinate square plus the v coordinate square. So in practice, what we can do is we can basically average in concentric annuli in UV space. Okay, so we draw annuli and then we average the reals and the imaginaries and the weights within concentric annuli, and we plot them as a function of UV radius or UV distance. Okay, so that's what I'm doing in this line. I'm doing some concentric annuli averaging, and then I'm plotting here. And what you can see here is basically we have a 1D plot where we have the real, instead of the real being the color scale in 2D, now we've got the real as a 1D plot as a function of UV distance. And you can see that the reals, there's error bars here which are very small because the uncertainty in the data is quite small here compared to 100 millijansky. But you can see indeed that the value of the reals is flat at around 100 millijansky, which again indicates the presence of a point source. And if we plot the imaginaries, you can see that again, despite some noise, they're all hovering around 0, and then the noise increases at longer baselines. Why does it increase at longer baselines? Well, I think the main factor here is that as you get to longer baselines from the center, remember we're averaging in circular annuli. Basically, as you get to the longest baseline, you only have fewer sparser points that you're averaging, so your noise level would be intrinsically higher. And you can notice that because within concentric annuli you have many UV points, then by averaging, the noise goes down. So remember that the noise was about 4 to 10 millijansky per UV point. And now after radially averaging, you see that the noise is much lower than 4 to 10 millijansky. It's about, it's maybe like a few tenths of times smaller. So this is another advantage of this radial averaging, is that you're really driving down the noises. And if your source is centrally symmetric, at least in UV space, then this is really advantageous to try and detect things. Okay, so the UV analysis alone indicates the presence of a point source in the center of the field, if you didn't know before, with a flux of, 100 millijansky, because I manually changed it to 100 millijansky. But so what would it look like if the source was offset from the center of the field? Remember what we said before, that if a source is offset, so here I've manually offset the star from the center of the field, of the observations. And remember what happens then is that we're introducing a phase shift in the visibilities. And a phase shift in the visibilities means that the real part becomes a cosine with amplitude equal to the flux of our source, and the imaginary becomes a sine function. So the cosine function here, you see it's about 100 at the origin, so it's a cosine function, and 100 is the flux of the star. Whereas the real is a sine function, so it's 0 at the origin and then oscillates as a function of time. Right. What we will do on this. Okay, so that's what we're seeing. Now, what is the direction of the offset that I inserted, right? Just by looking at the visibilities, if I didn't insert the offset myself, you could have guessed what direction the offset was, but because you see that this wave is along the U direction, so what that means is that the offset of the star is from the phase center is along the RA direction in the sky. Okay, so just from the direction of this sinusoid, you can basically infer the direction of the offset, and furthermore, you can infer its period. So the period of the sinusoid, so for example, here in the imaginary, so it's 0 here at the center, and then it's 0 again after full period at about 70 kilolambda. Okay, so the period of that wave is about 70 kilolambda, and the 70 kilolambda, it turns out, is related to the offset of the point source. So the point source is offset by 1 over this period in kilolambda. So the offset is 1 over 70 E3, so 70 kilolambda in radians, or if you turn it into arcsecond, is offset about 3 arcseconds, and as we said, along the RA direction. That is indeed the offset that I've inserted. If the offset is, I'm not going to spend a lot of time on this, but if the offset is along a 30-degree position angle instead, you will see that the sinusoid is at 30 degrees from the x-axis. So again, you can tell what the offset is by just looking at the UV, at the sinusoid in the UV space. Okay. So if instead you have a ring morphology, if like me, you look at circumstellar disks or circumstellar rings, what we can do is we can create a model of the image. So what I did here is I just created a ring and plotted it in Python with a radius of 4 arcseconds and with a 0.5 arcsecond and a flux density of, again, 100 millijensky. So here's my ring. And what I did then is I used NumPy's fast Fourier transform routines to see what its Fourier transform looks like. And as you would predict analytically, you can actually do this Fourier transform analytically. You get a Bessel function of 0th order as the Fourier transform of that. So our visibility function corresponding to a ring in image space is a 0th order Bessel function, as shown here in UV space. So if I now azimuthally average in concentric annuli, like I did before for the point source case, let's see. Oh, I didn't run this bit. Okay. Yeah, so you can see that now we're getting this oscillating function that corresponds to a 0th order Bessel function. And for a Bessel function, we know that the 0 location is given by, so here we go, that the real part of visibility goes as a Bessel function of 0th order, and we know that the first 0 happens at 2 pi rq, which is the x basically of the Bessel function, happens at a value of 2.4048. So if we equate the two, then we can basically use the first null, which is this q value. So q is the UV distance, r is the radius of the ring in the image plane. So basically, the first 0 of the Bessel function tells us what the radius of this ring is in the image plane. So without having to do any imaging, if we looked at our data and it looked like a Bessel function as a function of UV distance, we could just infer that it's a ring, and by looking at the first null, we can basically infer its radius. So the first null here is at around 19.7 kilolambda, which if you extract r from this equation, where q is 19.7 kilolambda, you get that the ring radius is indeed 4 arcseconds. And again, the imaginary is 0 because it's centrally symmetric, and the ring I create is centrally symmetric and centered on the origin. So in general, you can fit in UV space. You can see that if you can create your own morphology in Python or whichever way you want, and you can basically create a parameterized model image of what you expect your object to look like. Then you can Fourier transform to obtain the visibility function, like I did here, getting a Bessel function. And then what you can do is you can evaluate. In a real case, you could evaluate or interpolate this model visibility function at the UV locations of your data, and then you can compare directly the real and imaginaries from your model to the real imaginaries from your data. Given and using the noise in the data as well through the weights, you can basically run a fit in UV space. And there are some advantages to running fits directly in UV space. There are also some cons. So there are pros and cons to this non-imaging analysis. So the UV analysis accounts, first of all, for the inevitably missing short spatial frequencies. So the inner hole in this, where is it? The inner hole in the UV coverage, which is inevitably going to be there, and that you're not going to know about it if you just look at your image. And that's particularly important for spatially extended sources, where a lot of it, their flux will be concentrated in this missing UV spacings. Additionally, visibilities have very well characterized noise properties. They're independent of one another, so every point in UV space is independent of one another, and the noise is close to Gaussian. On the other hand, pixels in the image are correlated due to the beam, so they're not independent of one another, and that can be hard to account for in fitting routines. And particularly gridding and deconvolution during imaging, like with clean, affects images in a non-linear way and can create artifacts. And so remember that the cleaning procedure is basically almost like fitting a model to a data, And so in a way, if you're fitting clean images, what you're doing is fitting a model to a model. And so that's probably not what you want to do. On the other hand, the visibility analysis so the visibility analysis advantage say you don't have this problem, but of course, visibility analysis is infeasible if you have complex structure, and which is hard to picture in UV space. So if you have many point sources, or you have really complex structure that is hard to analytically think of what their Fourier transform would be, then you really need to practically carry out imaging, at least to get an idea of the source structure before you go further into UV analysis. And that's generally done all the time. So although we can start getting an idea before you even carry out the imaging, we typically always carry out some imaging and then go ahead to try to interpret the data by fitting the visibility function directly. Okay, so I hope this was useful and it gave you a nice idea of what the visibility data really looks like, and try to make you a little bit more comfortable with it before you go into imaging. Okay, so thank you.